Okay, so I hope that most of you have been able to follow the discussion on the S matrix and why X matrix is nothing but basically this exponent or time order exponent of I VH0T as an operator, right? This is something that is an assignment problem. So I have mostly worked it out, and with minus I, sorry. So I hope this should be fine. This up to here, I hope that you have been able to digest. So what we are trying to see is, so the point of the S matrix is a transition amplitude, but the question is what exactly it is, how exactly it converts to something that is measurable. And to do that, it is basically a little bit useful to first go through cluster decomposition principle. But to motivate this, I think there is some very nice question that Priyanka sent me by email. So I would like her to ask that question herself, and maybe I can start by answering that question first, and then. So Priyanka, why don't you ask the question?
Yes, sir. So my question is related to entanglement. So as you said in cluster decomposition theorem, that even if two systems, one is in our universe and one is other is at outer universe, even if they are entangled, uh, even if
Okay, I understand. So you're saying that how it is consistent with correlations being
yes,
non-local.
quantum correlations, as we saw in Bell states.
Yeah. So for that, one needs to make two distinctions. So let us remember what was the Bell experiment originally was about. It was about having like a Bell pair, something like this. One by root two, and this is a state, which is a Bell pair. And suppose they are separated like this, and we measure the spin here and measure the spin here. This measurement A and B, and they would be. So if this is up here, it has to be down. If it is down here, it has to be up, right? So it will collapse into these two possibilities, and so in a way. But of course, this is simply. So it means that the measurement here and the measurement here are correlated. And the question probably is, how is this consistent with the cluster decomposition? Is that the question, Priyanka?
Yes, sir.
Okay. Well, this is, yeah, there are many ways to answer this question. Okay, so so first let us start with the statement of cluster decomposition itself, and okay, so here is the statement about cluster decomposition. The cluster decomposition doesn't say that nothing is correlated. That's not the statement of cluster decomposition. What it actually means is as follows: that if I take the time ordered product or any kind, that you can think of it in this way. Suppose I have O1x1, O2x2. Let me just start with 4 operators. Okay, and then what you should do is to say that, okay, so one important thing here in this Bell experiment, one has to realize that they're talking of correlations outside the light cone, because you do these measurements do not affect each other, they're independent measurements. But the fact that if you find result up here and the result will be down there, right? That's the main important statement. So the cluster decomposition principle is basically related to the fact that you can do such independent measurements that the measurement of one is not going to affect the other. So, which means that actually these independent measurements are correlated. The fact that you could do independent measurements, even if they are within the light cone, these two measurements would have been independent if they are quite far away. But of course, here it is also part of, okay, it's not only because of cluster decomposition, but also causality that these two measurements are independent. Actually, one cannot affect the other. And the correlations are being stated in this way from the Bell pair point of view. Whereas here, the actual statement of cluster decomposition, what I meant was that if you do this, you will have basically write down in some kind of diagrams of this kind. Say one example is this. So these things you see are connected, that so all of this x1, x2, x3, x4 are connected to each other. So this is called connected. And this is like one class, which I call T connected, x1, x2, x3, x4, all of these are connected. And then there will be stuff which are like this, x1, x2, x3, x4, and x1, x3, x2, x4, and then x1, x1, x4, x2, x3. Connect. There are three kinds of this thing, and some corrections on top of that, maybe. And then there would be so then these are like these class of diagrams where this is essentially TC x1, x2, TC x3, x4, the connected parts, plus two other terms. And finally, you will also have terms of this kind, like one-point functions like TC x1 and TC x2, x3, x4. So these diagrams would do look like this, x1, and then, sorry, this is simply a tadpole. So it has only one x1, and this is one loop that suppose, and then here you will have some connected diagrams of this kind, x2, x3, x4. And then there are two other terms like, sorry, there are three other, no, here there are two other terms, and here there would be three other terms, right? So essentially you will have all these kinds of terms where everything is connected, where everything is not connected. Now, what is happening here? So in this class of diagrams, so in this connected part, if any one of this, if say x1 becomes far away from x1 is say far away from x2, x3, x4, then typically this correlation function vanishes. What I mean by far away is that that these things are large. Mod of x1 minus x2 square is large. Things like that. So basically, they are not within the light cone. So on the light cone, things are different. So that they're not light-like separated, and one of them is far away from the other. And in this case, what is going to happen is these kind of correlation functions are simply going to vanish. What survives are these things. So suppose if x1, x2 is far away from x3, x4, either spatially or temporarily, or in time, then these two, so only this will survive, and the rest will be similarly connected, would vanish. So suppose x1 and x2 are close together, and x3 and x4 are close together, but both x1, x2 are separated from x3, x4, then only these terms survives and all the rest vanishes. So what it means is as follows. What actually you're trying to do here, what is operator algebra telling you? This operator algebra are telling you about whether you can do independent experiments at all, whether you can do independent measurements at all. For example, if I'm doing a spin measurement at two places like S1, I do a spin measurement at X1, I do a spin measurement at X2 at some other time T2, and some time T1. So these are two operators that I'm doing. So you can think the state is constant and the operators revolving time. So I'm measuring these two operators, one after the other. So in this case, this measurement would not be independent measurement, right? And I have to see it as an operator together, right? And this is so the cluster decomposition principle has to do with the possibility of doing independent measurements at all. And what we know is from the Bell pair experiment is that if x1 minus x2 square is greater than 0, just from causality alone, the order S1, S2, or S2, S1 doesn't matter. And these two are completely independent. They commute with each other. If they commute, they two are independent measurements that one can do. So in a way, it's of course, if the state is correlated, then those two measurements are correlated. That has to do with the state, not with the operator algebra itself. Does
so
that answer?
So you're saying that the cluster decomposition principle doesn't mean that there can't be correlations, just that the measurements are independent. Like they can be correlated. Yeah.
The measurements can be correlated, but these correlation has to do with the statement of the state that in that way, everything is correlated, of course, because the vacuum, even the vacuum of quantum field theory is a highly correlated state. So all measurements are correlated in the vacuum. So if I do a measurement, exactly. But that doesn't mean that I cannot do independent measurements. So what I'm going to talk about now is in the context of S matrix. What does it mean? And the fact that you can do particle physics experiment after all without knowing the state of the entire universe. Yeah.
So, but this expansion that you just did, where does it come from? Like, is it trivial or does it come from?
This is something that I jumped the wagon. I'm just trying to say we'll soon learn how to compute it, and we will see this is the way it works out. Okay. So we are after this. From the next lecture, we will go to how to compute this, and you will see that this automatically comes out. This kind of stuff.
Entanglement is non-local, right? Is it correct to say that?
Well, I mean, it depends. It is correct and it is not correct. So let me explain that a little bit better. So
how does special relativity and quantum field theory do with entanglement is my question, like in the general framework?
Well, of course, I mean, entanglement is a fact of quantum mechanics in general. As long as quantum mechanics is there, you cannot do away with entanglement. But entanglement is actually not only is simply a constant. Even in free quantum field theories, non-interacting quantum field theories, also you have entanglement. So the reason entanglement comes about is, suppose you want to look into the region A and a region B, and the complement of A, for example. In a local quantum field theory, the interactions, the entanglement is generated by the interactions just along here. Okay. So essentially, the entanglement is typically in the vacuum, in a vacuum state. So this is true only for vacuum. That the entanglement is simply proportional to the area of this region. If this is R, this is RC. Del R, the entanglement is proportional to, or the von Neumann entanglement entropy is simply proportional to del R, the area of the region that separates from its complement, because the interactions is simply a geometrical property, simply because the entanglement is generated because of interactions between just something here and just something, because interactions are local. And so the entanglement should only be proportional to the area because it scales with the area. Entanglement entropy, the von Neumann entanglement entropy. So that is how but this is true only for the vacuum, okay? If you look for excited states, then this is different because of this following reason, that you could think about just a bell pair like experiment. You have some excitation, and with time, one of this excitation is here and the other excitation goes here. So now there is some entanglement that is coming about because of just simply separation with time. Because suppose you generate some excitation here, then things move outside and things move and stay inside, and then the entanglement is going to change, because if there are things that are staying inside and things that are moving outside, they will be entangled because they're produced, say a pair of photons is produced here and one goes out, one stays in, then then they would be entangled, of course. And you are generating entanglement then not only because through the interactions here, but also through movement of degrees of freedom across the boundary, because this is a fake boundary anyway. So yeah, so entanglement is there, and entanglement is a very important property, or very good, very fundamental way to understand quantum field theories. And there are many such interesting quantities in quantum field theory. Also, something called relative entropy, how well you could distinguish two states based on observables localized in a causal domain of dependence of a region. Or so that is a very important concept. So all of these quantum information is very much relevant, of course, in quantum field theory. But cluster decomposition principle has nothing to do with entanglement per se. It simply tells you about what measurements are independent or what measurements are not. It doesn't say that the measurements are not correlated. So independent measurements simply mean that one can do this measurements, that these measurements are not being affected by those. The results of the measurement can certainly be correlated, and they are. I mean, but who cares? I mean, we are not trying to find out the entanglement of the vacuum in this we are simply. So now the question is, how does it translate to transition amplitudes?
So there is a difference between a correlation and independent measurements. Can you explain it a bit?
Well, I think I already said that. Okay, so correlation simply refers to the results of the measurement, and independent measurements means that these two measurements are like two coin toss. They are independent of each other. One is not affecting the other. You see? So here, what it means is that suppose I'm measuring some kind of time-ordered correlation function, okay, here. And it simply means that it's some operators that I'm applying, and these two are far away in space compared to, and each operator application of every operator can be thought of as a measurement if you wish, then these measurements are independent of each other, okay? In fact, let me try, even before going to the S matrix, let me try to remind you of one thing, and that will make this maybe clearer in this context. So it follows that suppose I have an S matrix, right, which is this matrix I showed to be equal to time order product of exponent minus I by h bar dt vh0t. By the way, Priyanka, have I answered your question now, or do you have something?
Yes, sir, it's fine.
Okay. So suppose, okay, so this is your vh0, and if I make vh0, if I change v to right, if I change v to delta v, right, then what is going to happen? If you then s would go to so this is what I call s tilde. S tilde would be simply time ordered exponent of minus I by h bar dt. Actually, I should write it in a better way. So this is something that you can go to my notes and all the exercises that you have done. So maybe I should write it in this way. In the first step that I remember, if you remember, this is all the algebra we already did. Someone scale minus I to the power n h bar to the power n. And v hat infinity minus infinity is nothing but this operator itself, right? And then delta v h0 tau 1 and delta v h0 tau 2, right? And what is this actually? This is nothing but equal to then So these are the manipulations that we already did. Do you recognize these manipulations now? Because it's something that we had already did. This is basically go back to my notes and you will recall these manipulations very easily. So what I did here was to say that if V goes to V plus delta V, then this is how it should occur. And you can look into how I derived this thing. There was a similar exercise that I did. If you remember, I went from U to U tilde, right? And I wrote U tilde in terms of U. So if you go back to my notes that I sent you, you can easily recognize all of these, right? And so basically what it means is as follows. Now if delta V is equal to say some G, let me write it this way, delta V, I should write it as delta V is equal to D4X, maybe I should write it as O hat. Suppose delta V is an operator of this kind, then it follows, if I substitute this here in this expression, and then it follows that if I look into delta S as an operator, delta to the power N, and then I look into, so some R, right? Let me put some other index R. So I put GX1, delta GX2, delta GXR, right? Then this object at G is equal to 0, I put G, when I take the derivative, I should get simply this thing. Minus I to the power R, H bar to the power R by, and no factorial R anymore because, sorry, there should be a factorial R here. There's a factorial N here. Sorry, factorial N here too. So this would be H bar to the power R. And then I would have time ordered product of O, but now in the Heisenberg representation with respect to the actual H, right? Not H naught, right? And then you have, sorry, maybe I should have put here, sorry. Okay, so what is it? So it simply tells you, so if S matrices have to do with changes in fundamental amplitudes, right? If S matrices do with change in the rate of transitions, then the derivative of this S matrix with respect to the coupling constants, right? And when I put G is equal to 0 is simply the time ordered product of the Heisenberg operators, the corresponding Heisenberg operators. So which means that as follows, so I can even put a matrix element if you like, and look at any transition amplitude, delta to the power R, alpha, beta, beta minus alpha plus, or beta plus alpha minus would be simply the equal to S beta alpha, right? As an operator, isn't it? So this would be equal to then implies is equal to, sorry, delta to the power R. This is at non-trivial G of X, non-trivial coupling constants, and then I take a take a functional derivative with respect to delta G R. Sorry, here the G is the same thing. Okay, you could even think of having different operators if you wish, but for the moment you can easily generalize this. So yeah, so I take simply derivatives with respect to the same coupling constant for the moment. And this at G equal to 0.
So
right?
it's beta minus alpha plus, right?
Beta. Oh, okay.
It's
How does it
beta
matter?
alpha.
I can always change my labels, right? What I call alpha, I can.
I mean,
the
yeah,
plus
if you're
should be
writing S
there, the
beta
minus.
alpha,
Yeah,
so
yeah.
you wrote
So,
S beta alpha.
this should be S alpha beta. Sorry. Yes. Yeah, this is S alpha beta. Thank you. Yes, so then this would be equal to the phi alpha, which is now, remember, it's a free state, the time ordered product of OH x1 to OH xn phi beta. So these are the eigenstates of the free Hamiltonian, and it's the time, but these are in the Heisenberg representation with respect to the full Hamiltonian, right? And then you have a time order product of these operators, and the expectation value with here is simply this. So that is what this is what we get. All right, and so you can go back to my notes and see this. So this is a very nice interpretation then, that the change in the transition amplitudes due to this extra localized perturbation would be this. Now, how does it go back to what I meant is as follows. Suppose, so it means, for example, that if I make some small changes, x1, x2 here, and then somewhere far away, some other changes, x3, x4. So these kind of things, so you will only pick up so only the factorized part of this thing would get affected, which because what we are going to see is that the part of the S matrix that is being affected is only the part that factorizes. That's a sum. There's a product of two connected terms. Okay, that is what we are going to show now. So so that depends also on the fact that these also factorizes. That if x1, x2 becomes far away from x3, x4, as I explained here, then because of this property, the only term that will survive is this one, right? Because if I look here, then these two here, x1 and x2 are far away, right? And but x2 is also far away from x3, x4. So in this connected part, this will go down, go to 0. So that if you take any connected part, then if any one or two of them becomes far away from the other, it goes to 0. That's the property of a connected part. Okay, so because of any propagator will decay with space and time separation. Okay, so this is the reason why the only thing that can survive here is this term, right? So essentially, if we are going to make these two very far apart, these two changes very far apart from these two changes, then again, the only part of the amplitude that it can get affected are something that happens here and something, it only picks up the factorized contributions. This is something that I'm going to, if it's not clear yet, we have to hold on a little bit. But essentially, you see that the only part that will happen is that this will factorize from here, and which would mean that you could insert a complete set of basis of states if you wish here, and then do it like that. So okay, I'm going to be a little bit more precise later, but for the moment, let us try to understand that okay. So the main statement here is that these two contributions, there's a factorization here, which is going to affect the transition rates only in this in a specific way. So for the moment, I would return to this discussion later in this context, but let us keep this part in mind, and we'll come back to it later. So now what I'm going to talk about is this consequences for the S matrix. Okay, so let's see that of the cluster decomposition principle. So first of all, why the cluster decomposition happens is as follows. So it's basically a consequence of this so-called Riemann-Lebesgue theorem. The statement is as follows. It's suppose we can start with this one-dimensional case. So suppose you have dp e to the power I p dot x times fp. You can put an h bar if you like. This is equal to, or f tilde x is f of x, and So it means that if for large x, f of x has to go to 0. If the Fourier transform has L1 integrable, L1 integrable means that you take the mod of this thing. The general LP integrable means that you are, or LM integrable means that you are taking a power m here. And L1 means that you are simply taking m is equal to 1. So like L2 functions are those whose mod square, if you integrate them, that will be finite. Okay. So L1 norm, so this is often called the L1 norm also of the function. So you can also the functions also form something called the function space where you can define norms, and L1 norm is one such norm. So basically, if such L1 functions, if that is a Fourier transform, then they should be if you take the limit, if you take the Fourier transforms, then f of x should vanish as mod x goes to infinity. They will decay at large x. So this is the concept. This is basically a Riemann-Lebesgue theorem. So now, as I said, let us apply this to something for the S matrix. So for the moment, let us think of an S matrix where you have two incoming particles. So maybe I should write that alpha is simply equal to, say, P1, P2. So this is alpha plus the incoming particle, and then beta minus is simply P1 prime, P2 prime. Okay. So 2 to 2 is simply two particles goes to two particles. That's the simplest case. So in that case, what we should do is as follows, that we should define the S matrix. Then I would write it in this way. So what I called as beta alpha, right? I can also write in this way as P1 prime, P2 prime, and they are scalar particles, say, without any spins. So we have this simple relating. So this means that this stands for beta and this stands for alpha. Okay, that's what I'm saying, writing. Explicitly, two particles to two particles, right? So now this again can be factorized, as I claimed, into two parts, which I call S connected, P1 prime, P2 prime, P1, P2. And then plus S connected P1 prime, and then vacuum times S connected. This actually vanishes simply by energy momentum conservation, right? Because each S has the delta as a delta. So you should remember the S matrix can be written as delta alpha minus beta is beta alpha minus 2 pi I delta epsilon alpha minus epsilon beta times T beta alpha, right? And I remember, as what I said is that because of momentum conservation, you could rewrite this in a better way, del to the power 4 del to the power 4, the sum of all the final momenta. So P1 is a 4 momenta now, which is basically square root of P1 square plus M1 square P1. This is the 4 momenta, and you have all the 4 momenta should be conserved. So P1 prime plus P2 prime minus P1 minus P2 times some M beta alpha. So that is true, right? That is generically true. So if you have P1 prime and vacuum, you can never conserve this, either momentum or energy. So this has no role. So, but what you can have is this, that plus SC P1 prime P1 and SC P2 prime P2 plus two other terms. Sorry, this P1, yes, P1, P2 prime, P2, and then you can have P1 prime, P2 plus one other term, sorry, only one other term. Okay, so these are the two possibilities. This is the way this thing should go. Now you see that here in this part, so the point is, if you take any connected part, so that's the general principle, is that the general principle of this matrix in a local quantum field theory, if you by definition, this is basically a way to define the connected component. So in a local, yeah.
Sir, your 4 vectors are without the bar and 3 vectors are always with the bar, right?
Yeah, exactly.
And sir, I don't like, so how can you group P1 prime and P1 together and P2 prime, P2 together? Like still there's no momentum conservation. Okay, you're saying in general energy momentum
They are
should be conserved.
exactly. So it means that the final particle is exactly the same as the initial particle. That's the only way you can occur, right? The final momentum and energy is this simply goes unchanged. Yeah. So this is a trivial example, but if I take like instead of 2 to 2, I take like 4 to 4, then it will become highly non-trivial. So so in a local QFT, any connected component.
So, sir, this occurs only in the case of elastic scattering. So we are not considering inelastic scattering here.
Well, P1, P2 prime to P1, P2 can be in elastic scattering too, right? So what happens in elastic scattering is that your momenta do not change, only the direction of the momenta will change, right? But in inelastic scattering, the momenta themselves can change. So that can be the energy of each particle after the scattering can change. So that is inelastic. Anyway, so in a local QFT, so I have not made any assumption about elastic versus inelastic, can be general thing. So in a local QFT, any connected component SC, P1, say, let me define it more generally, like P1, P2 prime, PM prime. There are M particles in the final state, and there are N particles in the initial state, Pn. So this would be proportional to delta to the power 4, P1 prime to plus PM, sorry, now it's a 4 momentum, PM prime minus P1 minus Pn. So 4 momenta are conserved times M beta alpha, where M beta alpha is a function of all the momentums, P1 prime to PM prime. So where M beta alpha is of L1 norm. Okay, so which means that mod of M beta alpha, if I integrate over all momentum, d cube P1 prime to d cube PM prime and d cube P1 to d cube PM, this is less than infinity. So essentially that's the statement. This is not quite true if you have massless particles in your theory, but then what you need to do is to not consider this M beta alpha themselves, but a more of a measurable M beta alpha, where you integrate over some final states. Because if you have massless particles in a final state, you cannot distinguish between, say, an electron and an electron moving and you have some photons which have momenta which are parallel to the electron, but with very low frequency. They are very low energy, so you cannot really distinguish the state because you can never measure the electron momenta very, very precisely. So you have to integrate over a range of final states. And if I do that, then again, this is true. So anything that is, so M beta alpha is what will turn out to be the measurable things are true. So now it's very important that that no subset of PIs, no subset of okay, maybe that energy and momentum are not conserved in a subset. So which means that if I take like, it can happen that if I take like 2 of these are equal to like 3 of these, right? So what can happen is the way I can satisfy this thing is also that if I take P1 prime plus P2 prime. So, okay, so what I meant, okay, so maybe I should have, okay, so I should have told this a little bit later. Okay, sorry, I think I'm, yeah. So, okay, what I want to say is as follows, that this is general definition of the connected component, that any connected component will have this property, that if I look at the connected component of the S matrix, it will be a single delta function multiplied by some m beta alpha, right? So suppose now, if that's what I wanted to say, suppose now, if say P1 prime, P1 prime plus P2 prime, maybe I should write it this way. If suppose P1 prime plus P2 prime is equal to P1 plus P2 plus P3, and then P3 prime plus PM prime is equal to P4 plus Pn. So suppose this is the way it works out. So separately, the energy and momenta are conserved between the two sets, right? So in this case, one can have contributions from also, so let me write down the, since I'm writing it this way, P1 prime, P2 prime, P1, P2, P3, and SC P3 prime, PM prime, P4, PM. So what I mean to say is as follows. So in such, if I'm looking at some experiment and I have, so if I look at like m particles going to n particles, only in a very tiny subset of this final states, I will find such things that there are energy momentum conservation within some subsets on their own, right? Generically, if I take arbitrary final momenta, if I keep my initial momenta fixed and I take an arbitrary final momenta, I will find that there is no such thing that happens. Only for very special final momenta, I will see this. So these are what I call non-generic. Because you see that these things are proportional, so there would be two separate delta functions. Then one delta to the power 4, P1 prime plus P2 prime, plus P1 plus P minus P1 minus P2 minus P3, and here delta to the power 4, these things, P1, P3 plus PM minus P4, P3 prime plus PM prime. So you have two delta functions, right? Now suppose this connected component contributed there, right? That would have been a contradiction because see, this part is L1 norm, right? And but this contribution is proportional to two delta functions, not one. One delta function is between conservation of this subset, and the other delta function is between this subset. So these kind of final momenta will get contribution only from product of these two connected components. So essentially what I'm trying to say is that you write the S matrix in general as a connected piece. Suppose I have say four.
So is there a specific mathematical description to the connected part, or you're just symbolically representing?
For the moment, only symbolically. When we know how to compute this, it will become clear.
So what exactly is SC then, even symbolically speaking?
Symbolically speaking is as follows. It will be proportional to a single delta function times something, some matrix element that is L1 norm, which means that if I integrate over all initial momenta and final momenta, the mod of this is a complex number, m beta alpha. If I integrate the mod of this, so this m beta alpha is a function also of okay. So m beta alpha is also a function of all initial momenta and all final momenta. If I take the mod of that, the modulus of that, integrate over all initial and final momenta, it should be of L1 norm.
Okay, so connected just means that the set of P1 to PM to P1 prime to PM prime, they obey energy momentum conservation. In that sense, they're connected.
Well,
you might have other subsets which are
as a whole. So okay, let me give a more general definition of it. Just let me give this example. It should become clear what I mean by connected. Then I have 4 initial particles and 4 final particles, right? So basically I have S P1 prime, P4 prime, and P1, P4, right? So this I can write down in this way. So one case is simply delta alpha beta, that all of these initial momenta are exactly equal to the final momenta, that P1 is equal to P1 prime, P2 is equal to P2 prime, right? So this is basically then delta P1 prime minus P1, delta P2 prime minus P2, delta P3 prime minus. So you remember we have this thing, right? S matrix always delta alpha beta minus, so this delta alpha beta is always there, right? So which means that it is simply nothing happens. There is no interaction at all. Okay, this is the first contribution that we should definitely get. And what are the next contributions? So the other possibility is that, so instead of having a total delta function, I can have product of two delta function, right? So that's equivalent to one delta function. And okay, so let me see, let me write it this way and it should become clear. So for example, I write it in this way, that delta to the power 4, okay, all of these are delta to the power 4. So these delta function will always be there. Sorry, this is P1, P2, P3, P4. And then, but suppose I also have a subset where it is conserved. So then I can write P1 prime plus P2 prime minus P1 minus P2. Now, if I take this together, it means that automatically, if I substitute this value here, it means that P3 prime plus P4 prime is equal to P3 plus P4, because I have a total conservation and have a conservation in the subset, which means the complementary thing should be conserved, right? So that is like the product of two delta functions. And then I can have some M, right? Now, the point that I'm trying to make is that this M can be factorized. If it comes from a local quantum field theory, then we will see that we can rewrite this as product of two M's. One is simply 1, 2, 1 prime, 2 prime times M 3, 4. Sorry, I should have written it the other way. Sorry for this. 1 prime, 2 prime, 1, 2, M 3 prime, 4 prime, 3, 4. Okay. So then there would be two more things like this, right? How many? So 1 prime, 2 prime can go with 1, 2. How many subsets? 4C2 kind of subsets, right? 4C2. So 4C2 means 6. So there are 5 other terms, which is 5 other terms possible. Because 1 prime, 2 prime can either go with 1, 2, or it can go with like 1, 3 or 1, 4, and then 2, 3, 2, 4, and then 3, 4. These are the 6 possibilities. So we have 6 terms, right? And then, of course, there are other possibilities. So, of course, we could have other things like 1 goes to 1, 1 goes to 1 prime, and 2, 3, 4 goes to 2 prime, 3 prime, 4 prime, right? There are these possibilities. So they're all possible such things. And in the end, you simply have one overall thing, which is delta 2 pi I, delta to the power 4, P1 plus P2 prime plus P3 prime plus P4 prime, minus P1, P2 minus P3, P4, multiplied by M1 prime, 2 prime, 3 prime, 4 prime, 1, 2, 3, 4. So I should call these M's connected, or C, to give a connected name. So essentially what is going to happen, this M with this delta would pair up to make one S connected, and this one would make, so there's you see that the full S matrix should have this structure. That's the statement I'm going to say, without any proof, that is how in local quantum field theory, the S matrices always behave. Okay, is this definition clear? So the main point is that these, I don't know who is calling. So sorry to go back. So the main point that I want to make is that in each of these connected components, MC alpha beta has no delta function. If there was a delta function, it wouldn't have been of L1 norm. If I integrate a delta function, say I integrate delta of P1 plus P2 prime, right? Minus, or maybe I should just simply take an example of this kind. Say I multiply delta P1 prime minus P1 delta cube with respect to P1 prime and P1 like this. The answer is simply infinity, because the first integral gives me 1, and when I integrate the other, I get infinity. So this is not of L1 norm, right? So therefore, MC alpha beta cannot have any further delta function. Okay, so it means that the full thing is 1, 2, 3, 4, 1 prime, 2 prime, 3 prime, 4 prime, 1, 2, 3, 4 should then factorize into simply S connected 1, 2, 3, 4, 1 prime, 2 prime, 3 prime, 4 prime, 1, 2, 3, 4 plus SC say 1 prime 1, SC 2 prime, 3 prime, 4 prime, 2, 3, 4 plus other terms of this kind plus SC 1 prime, 2 prime, 1, 2 SC 2, 3 prime, 4 prime, 3, 4 plus other terms of other terms of this kind. Okay, so this would be the factorization of this matrix, and each of these connected components has a single delta function, including this has a single delta function, and the single delta function multiplies something that is of L1 norm. Okay,
So where does the Riemann-Lebesgue theorem come in then?
now it is going to come. So far I have not.
And where is T beta alpha, sir? Like you're saying that this is the claim you're making and you'll derive it from the T beta alpha definition. Or,
yeah, so T beta alphas are going to have this momentum conservation included. And then it will be something M alpha.
E beta alpha has separately delta E beta minus E alpha is separately there, right? So why will T beta?
No, look, all that I'm trying to say is that, yeah, so of course, if you have momentum conservation in a subset, then you automatically also have the, yeah, so of course it doesn't preclude. Okay, you need, of course, so your question is about,
no, like delta E beta minus E alpha was separate from T beta alpha, right? Like it was. Yeah. So E beta minus E alpha generalized to the 4 energy momentum, and so why will T beta alpha have energy momentum term?
Well, the point is as follows, that it is not. But what I said is as follows. So suppose your M beta alpha has. So the way it works out is that the M beta alpha itself, each connected component will conserve the full 4 momentum. And you can always write the full delta, the delta function, right? The delta function of E beta minus E alpha as like a total delta times some separate delta function of the subset. Okay, let me maybe try to answer this in a better way without going more easier way to answer this is simply that
proof for this connected.
Yeah, there's a proof that. Yeah, this proof is simply comes from the way when we learn how to compute it, this will be rather automatic.
But you are not going to show like this.
Well, of course, when we learn to compute this thing, automatically see the structure without any difficulty. So that would be obvious. No, the question that you asked is about the M beta alphas are supposed to only have the delta functions for the momentum. So how come you also get a separate delta function for the energy conservation? Is that the question?
So I don't even understand where the M comes from. I'm still stuck at the T beta alpha definition. Like, I don't know what M beta alpha signifies. For me, it's just
no. All that I'm saying is as follows. So remember, so delta E beta minus E alpha. E beta minus E alpha is nothing that is equivalent to delta P1 0 plus P1 prime 0 plus P2 prime the sum over all initial energies minus P1 0 minus up to minus Pn 0, right? This is the meaning of this delta E beta minus the total,
yes,
the 4th component conservation. And then you have T beta alpha. The T beta alpha will separately have a momentum conservation.
Okay.
Yeah, so that has to be there. So now that's, yeah.
Yeah.
And then
so
this
you're
would be
saying like,
something multiplying in beta alpha.
so you're saying like you may have additional terms which conserve energy momentum in subsets or only momentum in subsets, the 3 momentum in subsets.
Well, what I meant to say is the four momenta are conserved only in subsets.
Okay.
So that is a statement here. Each of this has a single delta function, and the delta function is in the 4 momenta, right? That's what I meant. So it means that the 4 momenta of 1 should be equal to the same 4 momenta of 1 prime. The 4 momenta of 2, 3, 4 has to be equal to total 4 momenta of 2 prime, 3 prime, 4 prime here.
But like
Okay.
anyway, like the full addition should always be conserved. That's the ultimate, like 1, 2, 3, 4.
So of course, if it is conserved in subsets,
Correct.
then it is always conserved in total, right? That has to be there. So so what I'm talking about is, and then of course there's a delta function, okay, which is okay, these things, and then plus an overall simply delta, the product of deltas, which is simply that is delta alpha beta part, right? So this is how I'm trying to. You can always try to. So often what people do is that they take this 1 and write it on this side, and then write this in this way, so that you don't have to write the deltas anymore. So then so the 1 is always there, and then this part is going to factorize into, or is a sum of this kind of stuff, or sum of products of clusters. Okay, and each part is a cluster. That's one week. That is the meaning of cluster decomposition. Okay, so this is a very important statement, and this is only true for local quantum field theories, not in general. So the cluster decomposition is very hard to have a non-local or without using some notion of this quantum fields is very hard to get this kind of structure out of this matrix. Yeah. So what is the question again?
So what cluster decomposition have to do with the space-time distances being very, very large from each other? But
so for the moment, yeah, I'm coming to that. Okay, I understand the question. So just hold on for the moment. And yeah, I know what you're hinting at, because for the moment, we only have momenta. So now I'm going to use the Riemann-Liebeck theorem and show what it means in space and time. All right, so just hold on. So up to here, it is clear what I mean by the cluster, what I mean by a cluster. So
they are just
again,
pairs of momentum, energy momentum conservation pairs exactly. Of energy momentum conservation.
So yeah, exactly. So or in a more clear way, you have only, so suppose if I have something of this kind, like 1 prime 1 goes to, okay, let me try to make it. Okay, so far everything is fine. Okay, I'm going to. So what it means is that each of these clusters has a single delta function, and it multiplies something that has L1 norm. Okay, that's what I meant. Now, what is it? Suppose now I do the following exercise. I do a Fourier transform, which I call x1, x2, x3, or x3 prime, x4 prime, and then x1, x2, x3, x4 of this S matrix. So I have not included time here, but because to do the time, I have to do a different kind of a trick, and which I don't want to talk about right in the beginning. So for that, I would do dq p1 prime, dq p4 prime, dq p1, dq p4, and s p1, p2, p3, p4 prime, p1, p2, p3, p4. So look, what am I doing is simply a Fourier transformation of the S matrix. I'm simply Fourier transforming over the momenta. So now I can apply the Riemann-Liebeck theorem.
And then you see something, right?
Yeah.
Like exponentials, like you assumed it, or?
Sorry, I have to. No, thank you. No, yeah, I have to. I forgot to write them. E to the power minus I p1 prime dot x1 prime, so and so forth, and e to the power I p1 dot x1 is a by h bar here. Okay. Sorry, I forgot to write the exponentials. Yes, they want us to write the exponential. So I'll do the Fourier transform of this, okay? That's what I meant. And if I do the Fourier transform of this, then then I can apply the Riemann-Leibniz theorem. So suppose, if I do this thing on this object now, I have to first do it here and then do it for each of this separately. So suppose x1 prime, x2 prime, x1, x2 are very, very far from x1, x3, x4, x3 prime, x3, x4, okay? Suppose this happens, and then I do the integral. What does the Riemann-Leibniz theorem tell us? So let us first do this one. So this is a one single delta function multiplied by some in beta alpha. Now, this one single delta function essentially is proportional to the center of whatever it is. It is kind of irrelevant to this integration to this Fourier transform because it gives some overall factor. So what is important is that what remains is L1 norm. Since what remains is L1 norm, it simply implies that if any of this, if any subset here becomes far away from the subset there, it's a multivariable generalization of the Riemann-Leibniz theorem. It simply means that if any of the subset becomes far away from the other subset, then this S connected should go to 0. So this S connected will not contribute in this integral. Okay. So similarly, the only thing that can contribute is actually this, right? Even suppose if I take S1, 1 prime, 2 prime, 3, something like 3, 4, and S 3 prime, 4 prime, 1, 2, this is also not going to contribute because 3, 4 is far away from 1 prime, 2 prime. So this also goes away. The only thing that contributes is simply this, okay? So essentially, this would be the Fourier transform of SC, x1, x2, x1 prime, x2 prime, x1, x2, and SC of x3 prime, x4 prime, x3, x4. So which means that if this S matrix measurement is somewhat localized in space, right? Because the final particles are, the way to understand this S matrix is as follows, that they're basically, they're not like final states delocalized everywhere. Rather, you're taking the final states that you're taking, or final incoming and outgoing states, both are localized wave packets, right? That's how you're designing the experiments. So and in this context, these are the things, of course, there's infinite time. You need to assume infinite time. But in a way, you could actually generalize this and also put some time here. If you want. The S matrices in general means that anyway you have to wait for infinite time. So as far as S matrices measurements are concerned, it's very easy to see that then if I have a measurement here in Milky Way and a measurement here in Andromeda, it simply means that I have 3 prime, 4 prime, 3, 4 here, and 2 prime, 1 prime, 1, 2 here. And so this is where I start, I can look into this kind of thing and then convolute it with the initial wave packets or whatever. So in that case, of course, I only measure integrated versions of this. Further integration of x1 prime, x2 prime are implied. But the main point is that as long as the wave packets do not stretch further, if my initial wave packets are localized here and they don't stretch further, the integration explicitly is here and integration explicitly is there. So the only thing that contributes here is essentially the this kind of part, which means that we should have the processes that contribute are where P1 prime, P1 plus P2 is equal to P1 prime plus P2 prime, and here P3 plus P4 is equal to P3 prime plus P4 prime. So it means that the experimenter in Andromeda and experimenter in Milky Way are going to see the energy momentum conservation separately. The 4 momenta is being effectively conserved separately for these 2 experimenters. And although there could be a very highly correlated state, it doesn't matter, right? the experiments are simply going to factorize, simply because of the Riemann-Lebesgue theorem. The fact that we have, if we do this integral, if we do a Fourier transform, then the only thing that can contribute is this object, right? Because that's the only thing that survives when all of these points are far apart from all of the other points. Okay. So this is essentially the thing, because in other cases, because of the L1 norm, the integral should decay. That doesn't mean there is no contribution. There's of course a tiny contribution, but this is highly exponentially suppressed. Of course, it's completely irrelevant to for any practical purposes. Okay, is this clear? So this is essentially so it's basically, so if I want to review what I wanted to say today, it's a product of two things. The first thing is that if I look at an S matrix, it has this cluster decomposition property that it breaks up into clusters where each clusters have a separate momentum conservation multiplied by something that is L1 norm. Each has a cluster decomposition property of this kind. That's the first statement. And the second thing is the Riemann-Lebesgue theorem, which implies that if I do two experiments which are very far away in space, then these two S matrix scattering experiments will have to be independent of each other, because the four momenta are conserved on their own, right? That doesn't, okay, the fact that these two experiments are independent of each other simply means that that P1 plus P2 is equal to P1 plus P2 prime, and this measurement is not going to affect this measurement at all, right? That's what I meant. But the measurements of here can be correlated with the measurements of there if you start from a correlated state, right? Suppose you have a bell pair that moves here, another bell pair that moves there, right? Who cares? I mean, obviously, then the measurements, the results of this will be correlated with that. But that doesn't mean that I can interpret this experiment still independently of each other. So I can test the fundamental laws of physics just by staying on Milky Way. I don't have to take into account what others may be doing at some other galaxies. Okay. So this is a fundamental thing. So I make a distinction again between the fact that the measurements are independent and the fact that the measurements may be correlated. So correlations are there all over the universe, right? That's fine. That all has to do with what initial state the universe started from. If the universe, whatever it started from, it has then expanded, and all of these correlations are hidden everywhere. So all of this structure that in the universe that we see came up basically from some fluctuations over the vacuum, and that got embedded and seeded into like galaxies and structures that we see today. So there is correlations everywhere, of course, but who cares about them? I mean, that's not the point. I mean, of course, who cares about them? By that I mean is, depending on what the kind of questions that we are interested in. Suppose you're interested to test the fundamental laws by S matrix measurements, you don't need to take care of these correlations at all. I mean, they are there, but who cares? I mean, the actual measurements will factorize, even if some measurements are going. Okay, so basically what an experimentalist will always measure is a connected component of this matrix. So the basic lesson is that the reason we should look only to connected component of this matrix is simply because only so if I talk about a generic initial and final momenta, then these things anyway do not contribute, right? Why? Because suppose if I look at generic momenta, it will be highly unlikely that within a subset the four momentum is conserved, right? It is highly unlikely because it's only in very tiny zero measure subsets. If I do the full integration of final states, there only a zero measure of them in the sense of probability, I will be suddenly able to find some special momenta where they're conserved in subsets. For a generic case, the only thing that we do is here, right? And because if they're not conserved in subsets, they don't contribute because they're two delta functions. Only if they are conserved in subsets, they can contribute. So for this, only the connected component contributes anyway. And so as long as we look at the connected components, and that's what we typically do, they should be not influenced by anything else, right? They're simply stand on their own. And these are the things that we should be actually looking into. So an experimentalist, when they always look at generic momenta. They never talk about some exceptionally special momenta where they're conserved among subsets, okay? Okay, so now with this lesson,
Sir, could you go to that picture where you drew two galaxies? Sir, now in S matrix, the starting point was we have like wave packets which are separated and then they interact. But here, since they are far apart, they anyway don't interact. So you should obviously look at them independently, right? Like that's the statement I think you're trying to make, that they factorize. That's specifically because that's understood because in S matrix, the non-trivial term is interaction term, and interaction is removed here because they're far apart. So isn't that a trivial tautology or something? It's not, I don't understand. R1.
No, it is not a trivial result. So the point is that if interactions are local, you have this structure, right? But it's something that you should still show it. It's still a non-trivial statement that such a structure will exist.
1, 2, and 3, and 4 interacting? Like in that picture, are 1, 2, 3, and 4 interacting, giving 1 prime 2?
Well, they are interacting. They do interact. The point is that, okay, if you want to see it in this way, pictorially how it happens, suppose you have 1, 2, 3, 4, something like this, and you can have exchange here and then an exchange here. Say.
Okay, we are talking.
So this would be a connected diagram. This would be a connected diagram, right? But the point is that if these are separated far away from these two, then this thing will, because they're far apart, influence is small.
The interaction is there, but it's actually there, but it's small because they're highly far apart.
Yeah. So this is a virtual particle being emitted by this particle and absorbed by this. But because we are looking, the experiment itself is such that you already know what final state you're looking into, right? You're looking into a final state that comes out of and materializes in the detector, right?
Yeah,
it is on the detector on Earth. So if that is the case, there's a very tiny probability, of course, it will materialize in Andromeda, but that is a completely ridiculously tiny probability. And those kind of tiny probabilities are actually taken into account by these kind of connected diagrams. But this thing goes to zero. It goes, so you can estimate how long it should be. It will be m times r, right? Where I'm using the units where h bar is equal to c is equal to 1. So in those kind of units like mr, and then it will be highly, basically the r would be effectively the Compton wavelength of the virtual particle that is being exchanged. Outside of that is extremely tiny. And you know how the Compton wavelength scales, like it is such a tiny length scale, like of the order of say it's like a femtometer, say for a proton and things like that. So if you have that kind of a scale, and if you compare like astronomical distances, this is like such a tiny number that it's outside the machine precision of even the most robust computer that you can ever find of the size scale of the galaxy. So it's an extremely tiny number. So it's we can completely forget about it. And
so this is the consequence of the Riemann-Lebesgue theorem, like this disconnect between the 1, 2, and
it's a consequence. It's a structure that the structure in momentum space implies such a thing in real space.
Real space.
Yeah. Okay. So this is something that you need. So what you need to show that you have this cluster decomposition property from a local quantum field theory, right? This is something that you need to show. If you are able to show that, then this will follow. The cluster decomposition, the independence of the measurements will follow. Sorry, although the measurements can be correlated, there will be independence. That you can what you mean by independent measurements, independent experiments, is that you can simply interpret the experiment, you can simply draw conclusions from the experiment here without knowing what the experimenter did there, right? Well, that is also true for a bell pair. For example, I need to understand how one of the bell pair interacts. I can simply look at one, I can forget the other, what they do. Of course, the measurements there would be correlated with the measurements I will do there, but that's irrelevant. Okay, but in the quantum field theory, it's a very important, it's a very non-trivial statement, because you see, in quantum field theory, I just completely got rid of x or anything. I simply talk about very abstract things like there is some fields and a field that permeates the universe, and if I vibrate the field, I get all kinds of structures which have indefinite number of particles. It's a superposition of different number of particles. And so it's a very highly non-trivial structure that, and that you can recover this independence is highly non-trivial actually. So what people wanted to do at one point of time, they wanted to develop something called the S matrix theory. They said, let us forget about quantum fields. Let's only talk about S matrices, because the logic for that was that after all, the S matrices are being generated. I mean, the S matrices are the fundamental processes. If of anything can be understood in terms of S matrices, right? And they are any kind of physical process. So let us talk only of S matrices and not about fields or any of this garbage, right? And then they said that let us try to define a set of rules that S matrices should satisfy, and then we are done. Let us not talk about quantum fields anymore. So then they started to see, like, do that, and this is something called the Bootstrap program that was started in that context, and it's called S matrix Bootstrap. But then people were very hard to recover this cluster decomposition property. You can start with this bunch of rules, but if you you have to put in something there to get this cluster decomposition, which actually brings back the quantum field back into picture. So it's very hard to do away with quantum fields or to recover this kind of. So
here, where did they use quantum field theory?
The fact that interactions are local, that you can draw these diagrams,
but that's a postulate
from quantum.
The local
so
interaction.
It's certainly a postulate, right? That's what I'm saying, that without this postulate, it's very hard to get this cluster decomposition.
Okay.
What I'm trying to say is that without using such a quantum field theory structure, if you just say that I want to, okay, there are many things people put in, like crossing symmetry, this and that, and many other non-trivial structure on S matrices. And then they try to say that, okay, if I put these kind of analytic rules, so all of this becomes very abstract, because you need to talk, like, analytically continue this S matrices into unphysical momenta, unphysical energies, and all this. So, but nevertheless, people want to just simply constrain the properties of S matrix such that you recover all the answers that would have got through quantum field theory. And it's not like it is not completely successful. This program has been revived now by some people in Princeton, Nimar Kami Hamed and many other people. And there are many other, some few Indians also working on it. It's a popular program in many ways. But now the aim is not to replace quantum field theory as such, but rather to get a better understanding of it, or get a better understanding of something that you do not see already from the Lagrangian. So in fact, what people find is that when you try to, the S matrices of the theory know some more deeper symmetries or deeper properties of the theory that is not evident from the Lagrangian. In the Lagrangian, you might see some symmetries, but in the S matrix, there's some deeper symmetries that you don't see okay. So I mean, and then people have been also able to do this, that sometimes quantum field theory computations can be first lifted to a string theory computation, and then you can take some limit when string theory becomes quantum field theory. So just like there is a limit where quantum physics becomes classical physics when you take h bar goes to 0. And sometimes people have been able to recover this rather beautiful properties of S matrices, which are not present in the Lagrangian, just from such a limit of string theory. And then it turns out that instead of writing this matrix as sum over different Feynman diagrams, you could get the total answer in one go, just based on some very magical properties. So this is a very current goal of research. But the point is that if you want to say why the cluster decomposition principle is obeyed, you somehow have to go back to these Feynman diagrams. That you have to say that there is some kind of Feynman diagram like description. And if the graph is connected, it gives rise to a connected component of this matrix. Okay, so that's what we will see. Whereas if there is no, if the disconnected graphs where there is no interaction between this set and that set would give rise to this. So essentially, it means that we can simply use the independent measurements simply mean that I can simply just collect all the Feynman diagrams here and then do the Fourier transform of the legs and independently there. I don't have to, so to interpret this experiment, I can just do this calculation without bothering about what the other guy is getting. Although the results are correlated, they should be correlated, right? Or they could be correlated or should be correlated, doesn't matter. Okay, is this clear now? All right, so we don't have much time left, so maybe we should stop it here. And
we still haven't completely like seen the M beta alpha thing. You're saying it will come out when you expand and you will naturally see it later, but we haven't done that right yet.
No, we haven't done that yet. So that is where we will be going next. We will then now learn to compute these objects. Okay, that is what we will do. And so from the next class, I will start with, I'll go back again to the Schwinger-Queldish contour more generally, and also, so we'll learn how to do these computations in general. So the other topic that I wanted to complete today, but it didn't get through, was that I wanted to show how this S matrices actually translate into rates and cross sections that experimentalists measure. So that will only take half an hour of a class, but I think I can skip this part. Maybe I can come back to it later, or maybe I can, I can probably come back to this later when I actually do these computations, because for the moment it's a good place just to move on from here. So we will come back to this when we do some S matrices. It will be more fun then, just to see how then you can explicitly do some computation. You can try to actually calculate how many rate of events experimentalists would see, and then match it to experimental data and all this. So that will be more fun then, maybe, to do it once we know how to compute this M beta alpha. So I'll come back to that later then. Okay, so for the moment, we have some good idea about what the observables of the theory are and how we can connect them to correlation functions. So we talked about two kinds of things. Like one is simply the computations which are in observables, right? Where we have something like this, some state alpha, and then it goes and comes back beta. And here we have some U tilde and, or say U1, and here you have U2 dagger, something of this kind, which translates to putting operators, basically operator insertions on this side. And one such observable is the conductivity of a metal, because it involves a response function, it involves this commutator. And we will see some explicit examples there again. I think, again, I will talk about it when we know how to compute it, and then maybe it's more fun that way, explicitly how the conductivity of the metal will come out. And then the other class of observables is like this, where we have some alpha and some beta. And so it starts with some initial state, and it goes to some final state. And these are the S matrix type of things that we see. Yeah, and then we also talked about more general things, right, where we do this kind of. So the question that we will try to answer is, and so this kind of thing will be measuring quantum chaos, as I said before. So the question that we will try to answer is how to compute these things. And this is something that, again, we will start with basic quantum mechanics, because one going generalizing it to quantum field theory would not be very hard. It will be rather easy. Whereas the algebra is much simple if we look into, there's simply more indices to take care of. I mean, and also I think it's much easier to start with like a simple harmonic oscillator, and we'll do from there and try to. And so it looks like I'm not getting into quantum field theory yet, but we're already deep into quantum field theory, or simply don't know it yet. You already know a lot about quantum field theory already from this 8 lectures so far. A lot of non-trivial stuff. Yeah, okay. So the idea would be that first I tell you how to do this in quantum mechanics. Then I will talk about the Folk space, and talk about how to construct multi-particle, what is a real multi-particle state basis that we are using, introduce the quantum field, and I think I'll first introduce the quantum field and then talk about the Folk basis. This also in that sort of little bit reverse order than what is usually done. But things will become much clearer there, because if I just start with some formalism, it's not that fun. You basically, I think the idea is to get into it. So like, for example, what you would be, many people would learn how to do these computations, but not realize this nice property of cluster decomposition. You can, many people, you can do a course where you can simply tell them how to compute, but don't show this beautiful property. Then what's the fun? I think it's quite fun to show that indeed Milky Way. And so I think the idea would be to first understand the essence of a structure, like understand what is why a certain thing takes a certain form, and then try to go deeper. I think it's better to first know what to expect. So the backstory is sometimes more important than the formalism itself, and like why people do it this way. That's so one way to understand one interesting answer why quantum field theory is the right framework to understand particles, or to understand fundamental physics, is simply because it's something that naturally has this cluster decomposition property. Okay, so that would be the end of today's lecture from my side. Are there any further questions for today? Doesn't seem so. So Chinmaya and Lakshman, can you also put this lecture 18 in your notes, or that would be too much? Where are they? Lakshman is not here.
Yes, sir, we will try.
Okay, try. Because this lecture 8, it doesn't have too much content. It is just simply, it will be like some small pages. Okay, so, okay, but good. So we are proceeding a little bit slowly, but that's fine. Let me end recording then.